Welcome to the first episode of At the Workbench here at 4111 Spyglass. A full channel introduction is coming soon, but for now, here is the short version. We're building software and hardware stacks for controlling and monitoring autonomous vehicles. These weekly At the Workbench videos show what we build, how we build it, and what we learn along the way. You'll also see deeper technical dives and tutorials in separate videos. Right now, we're working toward getting two nodes to communicate using radio transceivers. Because this is a large feature, we're breaking into smaller testable steps. This week's step is simple. Take data arriving over USB and transmit it over radio. Just one node, just one direction, from USB to the radio. We're using the STM32 Blackpill, which gives us 512 kilobytes of flash and 128 kilobytes of RAM. Compared to the classic blue pill, the Blackpill is more capable, includes reset and boot buttons, and, importantly, supports flashing directly over USB. That makes iterations fast. For the RF side, we're using the ubiquitous blue CC1101 module. These boards cost only a few dollars and are advertised for 315, 433, 868 and 915 MHz. The CC1101 chip can operate across those bands, but the board layout and components are optimized for only one. The blue boards are optimized for 433 MHz. 433 MHz sits inside the ISM band in the ITU Region 1. ISM, Industrial, Scientific and Medical bands, are reserved internationally for low-power, license-free communication. Think garage door openers, key fobs, weather stations, and so on. So for Region 1, these blue CC1101 boards are perfect for experiments. In Region 2, however, the equivalent ISM band is higher up at 915 MHz. 433 MHz operation requires an amateur radio license. I have one, so I'm good to go. And for completeness, ISM allocations are ultimately defined by each country, not just the ITU region. This is particularly true in Region 3, so check your local band plan before transmitting. The first job is soldering headers on the Blackpill, so we can connect it to the CC1101 with jumper wires. The CC1101 pinout is straightforward. 3.3 volt and ground, SPI clock, MOSI, MISO and chip select, two digital lines, GD00 and GD02 for signaling transmission complete and receive data. Given the Blackpill pinout, I'm using pin A4 to A7 for SPI1 and pins B0 and B1 for the interrupt lines. The CC1101 uses a 2x4 header, so it won't plug into a breadboard. The Blackpill will, so we'll connect the two using DuPont cables with one male and one female end. I could have used pre-made wires, but I recently got a crimping kit and I could use the practice. Since pins A4 to A7 and pins B0, B1 are adjacent, I'm using a 1x6 housing. 3.3 volt and ground conveniently fit into a 1x2 housing. A quick continuity test ensures that any problems we hit later are software, not wiring related. And indeed, one crimp needed a second squeeze. With wiring confirmed, we move on to firmware. First, we configure the microcontroller. Enable the external 25 MHz crystal for stable USB and SPI clocks. Enable the USB and set the device class to CDC, a virtual serial port. Enable SPI1 on pins A5 to A7. Configure pin A4 as GPIO output and rename it SPI1 chip select. Configure pins B0 and B1 as external interrupts and rename them GDO0 and GDO2. Configure pin C13 as a GPIO output for the onboard LED. When saving, CubeMX warns about a clock configuration issue. Using the automatic repair clock option quickly fixes it. We want to receive data from USB and send it over radio. If we transmitted every byte immediately, the CC1101 would send a packet per byte, which is terrible for throughput. Instead, we buffer incoming USB data and transmit packets up to 64 bytes long. But if the USB stream is slow or intermittent, we don't want to wait forever, so we use a state machine for transmission. The state machine works like this. USB interrupts push incoming bytes into a buffer. When the buffer is sufficiently full or when a timeout expires, we start a transmission. We fill the CC1101 transmission buffer, send the transmission command, and wait for the radio to signal transmission complete. Then we return to idle and let the USB interrupts refill the buffer. Simple, deterministic, and easy to debug. We implement a small driver layer, register initialization, strobe commands for transmit, receive, reset, and sleep, SPI register read-write helpers, and buffer read-write helpers. This keeps the main firmware clean and avoids repetition. Initialization includes variable length packets, maximum payload size of 61 bytes, frequency data rate and modulation settings, and datasheet recommendations for register values for stability and performance. With state machine and small driver in place, we can compile and flash the node. I wrote a small command line tool that repeatedly sends a string over USB and throttles the data rate. I connected my oscilloscope to the SPI lines to observe the radio traffic, and I set up a software-defined radio to confirm radio transmissions. Yes, the transmitter works. On the waterfall display, we can see packets appearing as the USB stream flows. When we throttle the USB input, the waterfall pattern changes accordingly. On the node itself, the LED toggles each time a packet is transmitted. So we successfully transmitted USB data over radio. But does the transmission make sense? Can we receive it? Can we decode it? That's what we'll explore in the next episode. All the code for this episode is available in our GitHub repository. The link is on screen and in the description. Thanks for watching At the Workbench at 4111 Spyglass. See you next time.